I have divided my talk in two parts with a movie in between. I know that I'm talking to an audience which is French, so mainly French, or Italian, so we are rather mathematically oriented, but still we need to consider applications. As I'm getting old, I decided to try to give a talk about methods, and I will try also to tell you that these methods are really important for applications. So, last thing, but we will talk about in the second part, is that la camisole de force de Cauchy, the Cauchy straitjacket, in my opinion, it is impeaching us to develop in science. So I want to urge you, all of you, especially young people, to get rid of this straitjacket. I like very much because camisole de force, because this we say in Napoleon the same. So the idea that your arms cannot move because you are like this is very, very suggestive. Okay, so the ancient problem which we will try to attack and discuss is how to model complexity at micro level and how to find models at macro levels. We will try to discuss the differences, if any, between metamaterials and natural materials. Then everybody, I am old enough to have taught now 25 years to students what is stress, what is strain, and these things like that. And I must tell you that we must change these definitions if we want to proceed. Of course, I will not repeat, in my opinion. You accept it as default. I mean, in my opinion. And then I will try to show you, but this I will do immediately, how many engineering applications are waiting for the powerful theoretical and numerical modeling, which were started by an Italian scientist I will talk about, whose name is Gabriele Piola. Milton Greme and Andrei Cherkayev designed, and then a 3D printer built a material, this one, which has been called pentamaterial. This animal, in the neighborhood of reference configuration, is not able to exert shear. So it is very similar to a fluid. Then you have this animal. It is a bikilar metamaterial. It is made with a strange microstructure, and this one has a macroscopic behavior which in this moment also in Paris by Nicolas Offray and my past PhD student Giuseppe Rosi has been proven to be a second gradient material, purely second gradient material sometimes. This animal has a negative Poisson ratio. Look this. When you pull and the distance between this and this increases, this bar goes up, so with extension you get an increase of transverse area. So you get this effect. With Pierre Seppecher and Jean-Jacques Alibert, we proposed, and we will discuss a little bit more about this, a material which is purely second gradient material in the macroscopic description. I will tell you exactly what I mean with macroscopic second gradient macroscopic material. I show you this structure. This is a pantograph. You are maybe Felix did it before than me. I am rather old. I needed to copy the signature of my father, and this tool is doing very well this copy. You use one side for passing on the signature of somebody, and the other side is reproducing it with the same size. This animal we will discuss later. If this is a rev, this is an animal whose deformation energy does not depend on the matrix representing in standard continuum mechanics strain. So deformation needs to be described by something more complex than this. This is what I am working on, the metamaterial on which I'm working now. This is a very light material whose behavior is depicted by this picture, and this animal has a terrible resistance to damage and progress of damage, and I think this could be used in aeronautical engineering. Of course, you can have complexity from natural systems. This is a classical example of porosity with the picture with canals, empty and full spaces. This is not a coral. This is a kind of metallic structure which is naturally present in some aluminum alloys. This is a foam, a metallic foam. This is the zoom in a fiber, a material which naturally is constructed by strong fibers, and these are examples in more familiar maybe to the majority of you of flow in porous media. With Felix we wrote a paper and we hope publish in the National Journal of Mechanics and Physics of Solids, and we hope that this microstructure can be modeled with a second gradient model. We may be wrong, but we hope it is a good step towards the solution of this problem. This is flow, simulation of flow in this situation. Then my past PhD student, now postdoc Daria Scerrato, will talk about concrete and its complexity, which we described with non-Cauchy models. And then Ivan, Giorgio, and Luca Placidi will show you salt cavities in salt matrices. So we tried, our group, to develop some subjects towards application, even if solidly based on a theoretical vision. I hope that I can state these kind of things in presence of a French audience, because usually when you talk with Americans, they say that everything is practical. Okay, but I hope that the tradition started à l'École Polytechnique is not lost. Okay, so captatio benevolentiae, you should not attack me too much. Mathematics is the art of giving the same name to different things. This has been said by Henri Poincaré, ancien élève de l'École Polytechnique. Maybe, you know, French engineers are rather theoretical. Cauchy was an engineer, by the way. Okay, he was telling this in response to poetry is the art of giving different names to the same thing. Now I want to be a little bit provocative. This man is Richard Tupin. When sitting at this table in Montreal, he repeated this Poincaré sentence at least 20 times. I believed he was becoming senile. Instead, he wanted to send a message. The message is advanced material, architectured materials, optimized materials, metamaterials, smart materials, synthesized materials, multi-scale material, multi-complex material. Different names for the same thing. everybody needs its own flag for getting money, position, glory, and everybody wants to invent a different name. This is very dangerous for advancement of science. So I want to claim that all these concepts are more or less the same. On the other hand, also theoreticians like different names. So you will find generalized continua, microstructure continua, continua with microstrains, with microstretches, higher gradient continua, Cossera continua, middling continua. Again, different names for the same thing. We will discuss. Okay, I want to be provocative. Okay. I hope to be able to prove you that I am right. But anyway, this is a discrete model of fracture in a porous system which we are developing in this moment. This is a cellular automaton with infinite states, and Alessandro Della Corte and Antonio Battista will talk about these things to you in a presentation later on. Okay, so now I try to be more precise and to show you why. Of course, I started from the end. Maybe it is better if I go this way. Some of this picture I already shown you, but so metamaterials are materials for which you choose the equations, and then you synthesize the material whose behavior is governed by these equations. This is not new, because analog computers in the 40s were based on the same principle. You needed to solve some equations, and you built some circuits whose evolution was governed by your equations. So General Electric spent a lot of money for designing complex mechanical tools, having somebody designing the circuits which are the analog of these mechanical systems. So the problem of synthesis is an old problem. Now, we want exotic materials. Their behavior has been theoretically conceived, and then you built it. So you want something having negative Poisson ratio, and you built it. So it is the opposite of what has been done for many years in many cultural ambient. Usually you have a system and you find the equation for describing that system. Now you write the equations and then you look for the system which is governed by these equations. This is beautiful. This is typically Lagrangian. Okay? And Lagrange, you know, was Italian. Remember this. Okay, this is a metamaterial which has been used in aeronautical engineering. The picture is out of focus because they claim it is secret, but I printed something, the 3D fabric which I've shown you before is behaving in exactly the same way. I will skip a little bit on this because I more deeply discuss this with the other slides, but I want to underline that metamaterials have a behavior which is not found often in nature because they are based on very specific, geometrically and mechanically specific microstructure. Okay, this is a very beautiful, beautiful picture which wants to underline that you have different length scales. for this reason you have what is called multi-scale materials sometimes. Okay, now there is a problem. I will spend a few minutes about this now, because I want to underline this. If you have a microstructure, you could decide, I want to study the system using a detailed description of this microstructure. This morning I was said by Ivan that our numerical simulation was finally ended after 12 days and 8 hours. So even with the and I have a computer which is not the most powerful, but we call it Diablo. Okay? He's cooled with liquid. In my office, you can believe there is an airplane when it is working. Okay, it is rather powerful. You are not ready to describe in great detail systems which are very complicated at microscopic level. So you need a macro model which could be given by continuum mechanics. Okay? This will not only allow you to get a global overall description of the behavior of your system, but this will allow you to save a lot of time in computations. However, a student of mine told me several years ago, you have, for instance, a discrete system. Then you homogenize it, you get a continuum model, and then what you do? You discretize it again with finite elements. Why you are doing it? You could directly find a simplified discrete system. Okay? I have spoken with many specialists about discrete mathematics, and it seems that nobody is able to get this overall averaged behavior of discrete systems without passing through field equations. So this is a subject to be investigated by itself, and I am not daring to change the standard way of attacking the problem. This is again the pantographic microstructure, and look, this macro deformation implies zero deformation energy. Also this one. Also this one. So this means that if this is a rev, the deformation energy of this rev cannot be described with first gradient theories only. It is singular. Okay? What is astonishing, and I will try to tell you, is that this behavior was described very carefully by Gabriel Piola in a wonderful book written in 1848. Again, mathematics was much behind, much beyond, much better than every practical imagination. Okay? Okay, one important thing, my friend Pierre Sepacher was very bad and he wrote this paper without me, proves with gamma convergence theorems that when you homogenize a system in which you have high contrast in macroscopic properties, then you end for sure in the mathematical sense, with a continuum which is of higher gradient. Okay, when the size of the rev, some physical properties are diverging while others are vanishing. And this extra mathematical result was obtained in this other paper. Okay, then this we discussed already, also this one. Okay, now we need to describe continuum models. We need to introduce continuum models getting rid of Cauchy-Poisson straitjacket, we must recognize that stress is less fundamental than the concept of deformation and dissipated energy. We must get rid of the postulation of balance of everything is important. Do you need some extra term? You add the balance of something. This is very dangerous in science. Viola criticized the useless proliferation of principles which started, I'm sorry to say this to you, because of the point of view of Poisson. There was a big controversy between Viola and Poisson. I will tell you why Viola has lost. The modern epigoness of Poisson and Navier, Truesdell and his followers, were criticized violently by Rivlin, Midlin, and Paul Germain. And also continuum thermodynamics by Coleman and Knoll has been criticized in a statement by Viola. So, you know, this is an old story. Can you develop mechanics without thermodynamics? Coleman and Knoll claims that you cannot. Lagrange, Viola, Midlin, Rivlin, Paul Germain claim the opposite. And I believe that this party, the party of Lagrangian people, is the party who is right. Okay? By the way, I paid for this with a delay of my career of 4 or maybe 5 years. So now I'm old and I'm telling it openly. I already paid for this. Okay? Lagrangian postulation of mechanics is, in my opinion, Viola's contribution to continuum mechanics. These are the papers written by Viola, and I will tell you, are you sure that the most modern reference is the best one? The best reference is the best reference. And being modern doesn't mean being better. These books by Viola are so clear that I decided, with the help of some friends, including Antonio Gazzani, who is here, I decided to translate them into English. Now, I translated 800 pages of Viola's books into English using the style of Maxwell. I was inspired by the style of the English by Maxwell to translate the wonderful Italian of W. Viola. I will tell you at the end why Viola wanted to write in Italian. Okay, now the Italians who are here present will read the wonderful Italian, but I didn't manage to translate it into French. I tried, but at the end I had no time. So, since Lagrange managed to reduce all the questions of rational mechanics to the calculus of variation, the decision of insisting to avoid its use is similar to wish to behave as those who, being involved in the researches in higher geometry, instead of flying to use the formula taken from integral and differential calculus, stubbornly persist in using in a pedestrian way the synthetic methods. Everybody studied with the ruler and the, I forgot the name in English, compass, also in English, and the compass. If you can write a derivative, you can do everything in a better way. So he was underlining that in mechanics you need the calculus of variation. Proceeding in this way, one does not manage to get many results and highly risks to be wrong. It is instead convenient to persuade oneself that the more the demonstrations are likely to be suspected to be wrong, the greater is the part in which they are based on the simple reasoning. as the intuitive grasp of our reason is very limited, and very easily we are misled as soon as the elements of the question increase to a great number and are interconnected in a complex way. So this is the laudatio of mathematics. We need to use powerful methods which, representing the simultaneous and compendious expression of many principles, are able to act by gathering simultaneously the power of all of them differently from what happens usually in the logical reasoning, where the principles are used one by one. We need methods which, once reduced to well-determined and immutable processes, do not allow us to be deceived. Okay? Okay, then maybe we can skip these things. Those interested can go in the web, but I want to tell you that I have written with Nicolao Frey, Victor Eremeyev, Angelo Amadeo, and Giuseppe Rosi a paper whose introduction I translated from Italian, the introduction of Gabriel Piola. The reviewer did not discover this until later when I added the reference. So there are some ideas which were not developed since 1848, even if the book of Piola was available in Google Books and freely available everywhere in the States, for instance. Okay, there is a limit. You should not believe that I believe that Piola is the God doing everything. The poor Piola could not use the principle, the Levi-Civita tensor calculus. So, if you read the equation of Piola, you find formulas which are filling pages and pages. It has to be said that only a nobleman without any problem of food and money could spend his life in repeating these calculations until they got to the right result. But I will show you how you can reproduce Piola's reasoning using tensor calculus by Levi-Civita in few pages. So another thing we should say, why so many colleagues are against tensor calculus? I know that Paul Germain and Salançon oblige everybody à l'École Polytechnique to learn these tools. But I have heard persons telling that tensor calculus is nowadays useless for engineers. This is very dangerous. This is the beginning of another Middle Age. This is a tool which Piola himself would have. He writes somewhere, it happens not so seldom that new achievements by means of which a branch of applied mathematics was augmented do not appear immediately in the concept and the exposition free from lengthiness and superfluities. Okay. Poisson attacked violently Piola, telling that his calculations were too long for being reliable. Okay? So I believe that Piola would use tensor calculus. Okay, now I am calculating rather well my time. I will tell you that somebody in the past claimed that I'm not writing formulas enough in my presentations. Somebody else said that I'm writing too many formulas. So having, because of the choice of the organizers of this, a little bit more time, I decided to fill the presentation with formula and philosophy. So you will be able to blame me for both. La cinématique d'abord. You start with kinematical descriptors. Then you introduce Lagrangian action function. Eventually, you add Hamilton-Rayleigh dissipation potential. The set of admissible motions, you calculate the first variation of action functional, and you get the evolution equations, including boundary conditions. People using Truesdellian approach are in troubles. They always cannot find boundary conditions, and what they ask me all the time, you will not find boundary conditions. Integration by parts gives you natural boundary conditions. For Lagrangian mechanics, there is absolutely no problem in finding boundary conditions. So, this is what has been written by Piola, and I'm translating with modern formulas. You have kinetic energy, potential energy, surface potential energy, which is related to other externally applied forces. Okay, so you have the placement, the referential mass density. This is the Piola transport of density. You have the gradient of placement, the velocity field, and Ws is relative to the actions externally applied at the boundary. Consider that we are purely referential. There is nothing else, only referential description. You derive, integrate by parts, you get this equation. This is Piola stress and boundary conditions. Okay? So when you assume that the dependence on F is via C, okay, you get this equation, which is more familiar, maybe. Okay, this is the famous Piola stress tensor. Okay? Now, Piola wrote objectivity condition on this stress, but the Pullman had a matrix. So he wrote A, B, C, D, E, F, G, H, I, and then he proved symmetry. He needed to fight with different and difficult formulas, while the formulas I show you are very synthetic. Okay, then after he introduced Piola transport, and he wrote the equations written in the reference configuration, he wrote them in the Eulerian configuration. This is the only process which is left in the literature with Piola name. However, which is very important, in the literature they use it on the other side. They use it from passing from Euler to Lagrange. Why? Because they believe that so-called Cauchy stress tensor, this animal, is simpler. This is the bad luck we had because of the validity of tetrahedron argument. Actually, the dependence of force per unit area on the normal of Cauchy cut is a consequence of the integration by parts, which you can recover painfully with Cauchy tetrahedron. Okay, so this process, as it is, you can reproduce when the energy includes a term where second gradient of displacement appears. Dan and Serrin claims that this dependence is forbidden by the second principle of thermodynamics. The reason for which there is this misunderstanding, it will become clear when you integrate by parts. They miss a term, so they cannot find balance of energy in the correct way. So we By the way, I want to tell you this story, which is interesting. I presented these results to a PhD course I held last year in Rome, and in a given moment I believed that everything was written already in the literature. There is a part of this deduction which I couldn't find, so my student challenged me. They said, you said everything is Lagrangian, do it. And this is the reason for which at the end I published the paper I told you. Because for a while these are simply lecture notes. So this is the first variation. Now the technical detail is not so difficult. You must integrate by part one time here and two times there. Okay. So, to be honest, Piola is not considering second gradient materials only. He uses nth gradient materials. But he stops somewhere. So you integrate by parts, you apply divergence theorem, and what you get these terms which must appear in what is usually called balance of force. So this is the standard divergence of Piola stress, but you get minus divergence of an extra term. And this animal cannot be obtained in the standard format of Truesdell and Poisson. And these terms is crucial if you want to model at macro level microscopically complex systems. So actually nobody did conceive a large class of metamaterials simply because they could not see the equations which are needed to do it. They believed they were not possible. This is what is astonishing in this story. This term appeared already in Piola. I want to tell you that I was lucky because Piola was not integrating by part completely on the boundary of the body. So this paper which I published contains some original results. I confess you that we wrote this before reading Piola. So when I read Piola, I was very worried because discovering that my paper was included in a paper of 1848 could be a dramatic discovery. Luckily, and I will show you, Paul Germain and Midlin could perform integration by parts completely on the boundary, and what they found? They found this is standard Cauchy stress. This is a new term of Cauchy stress, but look here. You have the divergence on the surface of this projector parallel to the surface, and the n is the normal of the surface. So what you get, contact force, depend on the curvature of Cauchy cuts. And this is what you cannot include in Cauchy theories. And this is very important for capillarity, for metamaterials, and natural materials which are microscopically very complex. I invited here one American on the Italian side, Anil Misra, who by the way is not American, his origin is Indian of India, okay? He likes variational principles, so he's Italian for honorary reasons, okay? And he attacked a similar problem in which a natural system is proving to have contact forces depending on the curvature of Cauchy cuts. So this is very important in what we want to study now. Not only when you have a boundary with an edge, okay? In second gradient materials, you have a force per unit line appearing there. but it is not yet ended. This is found in Tupin, Midlin, and Paul Germain. You have another action. You have surface double forces. You have the dual in power of the normal gradient of virtual velocity. So not only you have a duality in power with the velocity, but you have a duality in power with the normal derivative of velocity. And this is what is called double force by Paul Germain. Double force. Okay? Cosera contact couples are the symmetric part of this double force. To give an example, if you have this microscopic structure and you have a pantograph, green arrows produce a double force, while blue arrows produce a force. So in such a structure, you can act on your system with boundary double forces. Look at the green arrows, they are not couples. However, they expend power in the elongation of the pantograph. Okay, so this is a micro-macro interpretation. Okay, so in this paper by Giuseppe Rosi, Ivan Georgian, and Victor Eremeyev, they studied second gradient capillary fluids. They wrote Lagrangian form. They described fluid dynamics in Lagrange description. And this was very powerful. And they got this is the Piola tensor for this kind of fluids. By the way, this was studied carefully by Pierre Casal in Marseille. So this equation he found with different methods. And you have this is a wave which is trapped at the fluid gas interface. And so you have this mass concentration at the interface, which is very easily described in terms of second gradient fluids. And this conceptual tool was given to us by Piola many centuries before this was applied. And in Lyon, I worked a little bit with Philippe Bois. He wanted me to study that material used in aeronautical engineering. They became crazy. They couldn't describe bias test. This is the picture of shear angle variation in bias test. And this is the numerical simulation based on Piola's second gradient theory. So I think that this look, I want to prove to you that I'm really crazy. And indeed, you may be right. But now I have some minutes left. I was rushing a little bit. And I tell you why Piola wrote in Italian. He could speak fluently German and French. He wrote in Italian because he wanted to prove that Italian language could be a language for science. And he paid for this. Okay? So I will oblige you to hear the force of destiny, which was the music he liked, and you will forgive me, I will read it in Italian, then in English. Ho già in pronto altro non breve scritto in continuazione dell'attuale e nutro desiderio di poter produrre anche ulteriori prove di fatto dell'esposta asserzione, ma qualunque sia per essere il termine a cui riusciranno le mie fatiche, tengo per fermo che il tempo farà ragione alle parole con le quali diedi cominciamento a questa memoria. Ok? Now, which this sounds very Italian, you can read it in English. Okay? I have read another work which is not short and which will continue the present one. Unfortunately, he died with an aneurysm. Okay? And I strongly desire to be able to produce ulterior factual evidence of the stated assertion. But whenever I will be able to conclude my work, and no matter how successful will be my own effort, I'm strongly persuaded that time will give reason to the words with which I started this memory. This is some message coming from the depth of history. We should be aware of it. Okay? Of course, young people will say I'm becoming senile and wasting my time with this thing. But, okay, so I am perfectly on time, and I stop the music. So maybe the criticism which was raised before can be expressed. Okay? Thanks a lot. So I think that somebody was criticizing me, no?
Jim, you have a question, I think so.
I have any question.
Okay.
I have understood.
You are?
I have understood.
Okay. So,
Oh, okay.
you are frightened, you are upset.
No. I still wonder myself how to interpret, the non-classical forces. It's not clear for the moment for me, with a second gradient theory in particular.
You mean the boundary conditions?
Yeah, when you integrate by parts, you've got some non-classical forces who are put away, at the hand of the boundary. So you try to give an interpretation with the pantograph, but in a general way, it's really not clear for me.
You are raising a serious problem which deserves serious investigation. The people in homogenization, Arthur Lebet helped me, the director of Navier Institute, Karam Saab, Samuel Forrest, Pierre Sepacher, myself. We are trying to find a general characterization starting from micro level of these boundary actions. Up to now, we can give you only examples. Everything is understood with Coursera media. You have a couple on the boundary. With pantographic structures, you have these actions which are clearly expending energy, so you need them in order to keep the balance of energy. Anil Misra was using a granular array, and he acted double displacement, a gradient of displacement on the boundary, and he calculated a non-vanishing energy inside. And we are starting to build piece after piece. Maybe it is not I will die before, but examples are available. However, maybe you will be only satisfied if we give you a formula. Starting from microscopic level, we give you a kind of filter, telling you this kind of micro deformation gives you second gradient terms. This kind of boundary conditions are double forces, and these other boundary conditions are standard forces. Paul Germain is suggesting the following. Do you believe that power is a linear functional on virtual velocity? continuous. He wrote a beautiful paper about functional analysis.
If you admit the virtual work principle, it's one of the first states. So if you admit this principle, do you admit this principle or not?
Of course, I was not using Verdi for not impressing you. I admit principle of virtual work.
On this point, are you telling us that the principle of virtual forces must not be used for this problem because it's the classical way to obtain?
No, I claim that the principle of virtual works is the basic principle of every mechanical theory.
Yes.
I agree with this. This is my position. Starting from Archytas of Tarentum, who wrote the first version of this, since then, every progress in mechanics was related to the right application of the principle of virtual work. Balance of this and balance of that is the multiplications of principles, and you are lost. Remember, D'Alembert said, forces are an obscure metaphysical concept which nobody can really understand. Are you measuring forces? You are measuring displacements.
I don't understand what you say, because we have a way to obtain the clarification on what is the virtual power principle. It's what is classically used. I don't understand.
For you, forces is what you write in the formula of power multiplying the virtual displacement. Then we agree. But you must accept that not only you have velocity, you have also derivatives of velocity, normal gradients of velocities. All these are appearing in the virtual power. If you accept this and you want to call everything which is multiplying virtual velocity, first force, second force, force of this kind or force of the other kind, we agree. Force is not the dual of velocity. It's the dual of its derivatives also. But to get a true interpretation, you need a micro-micro identification. This is true.
You come back to microscopic interpretation or observation. For instance, in granular materials, because we are very involved in granular materials, GDR beige. If you look at the shear bands, for instance, people agree with the fact that it lacks a characteristic length, linked to the thickness of the shear band. If you write the equation, it lacks the characteristic length. So a possibility to make X appear is to use more complex theory, enriched theory, Cauchy, second value. But it's not really natural. For instance, if you use Cauchy theory, it will involve local, as you said, local couple, punctual couple, as a contact between grains. So a question, for instance, is do such local couple exist or not? Can we measure, for instance?
I think that Anil will show you this interesting phenomena.
Different subject, but maybe I can ignore the
No, you can show him pictures. We are not so formal here. You can show him pictures. You know what? By the way, you should not believe that with second gradient theory you can do everything. You can have also an Erringen microstructure continuum. I mean, you need an extra descriptor of kinematics and something more in the energy. So you can have, we discussed with Anil 2 days maybe about this, you can have a group of grains, you press it and you get a macro deformation. However, if you average the micro deformation and you attribute this macro deformation to each elementary couple of grains, you don't find the right energy because you have some concentrations of energy in some grains, and in order to take into account of this concentration, you need a kind of micro stretch descriptor which carries 1/2 of the energy, for instance. So I could agree with you that second gradient theory maybe is not the appropriate one here or there. But the message is, write the kinematics, write the energy, and calculate the first variation. You find the equilibrium, or if you postulate least action principle, you find the evolution equations, and then you are happy. You find everything. Then you can a posteriori maybe interpret this as stress, double stress. You can try to find an interpretation. Historically, this happened. So we should follow what happened in history. Piola wrote Tn, and then people interpreted this in terms of force per unit area. He wrote this in 1820. And the book and the paper by Cauchy is 1824. Of course, I quarreled with Gérard Mogen. You know, French people are terrible. They will never accept Lagrange is Italian and that Cauchy did something after an Italian, of course. Also, they claim that Paris is more beautiful than Rome. I mean, you can say you are better organized. This is true. You have more positions, you are richer, you have the atomic energy plans, but you cannot tell that Rome is worse than Paris. I mean, go there and so you must be honest. What I want to say is that I don't believe that we can do everything with second gradient. This was the first easiest calculation to show you. However, I strongly believe that without principle of virtual work, you cannot proceed for discovering new things. So I know that you agree because...
comment on the particular point of obtaining generalized continuums from macromechanical approach. One way is to move to asymptotic periodic homogenization. Something about the time you want to make some development until higher order, and what you naturally obtain, I feel that you know that you obtain some gradient model.
Claude was here. I know him very well.
What I would like to point is that you can use that technique. You don't obtain this class of models. It's for that reason that I said before that I do not agree.
No.
When you say all this,
okay.
Exactly the same.
I don't know when I will be able to write a paper with Claude about this, because those who know him should agree with me that it's very difficult. But we agreed, and we did some calculations. His models can be shown to be equivalent to higher gradient continua.
It's possible that when you obtain this, you have no assumption on the kinematic at the macrostructural level. It's just because you cautious you are.
You want to say that you can deduce from micro theories which is the right macro kinematics. Okay, but I'm talking about how to build a macro theory. I never tried to tell you in this talk how you can do micro, macro identification. This is simply...
This will be the right way to answer the fundamental question that you are asking for.
I don't know, this is another philosophical subject. Piola, sorry, I want to be nationalistic today. Piola said, if you blindly try to find a target, you risk to miss it. Macro theories are your target. So it is better that you start building macro theories, then with your identification process you guess, conjecture, which is the right target for your micro theory, and in this way you are less often wrong.
But by doing that you must be very, very clever.
But you need believe me, identification processes made blindly needs that you are much better. You need to be Boltzmann. I remind you that the only rigorously macro theory deduced from micro theories is fluid Euler fluids by Boltzmann theory. Otherwise, nothing.